For those who have been in the peer annual meetings before, in the past 3, maybe 4 years, we have been holding these blind predictions. Every year we have something different. So this year actually it's very different because it's an international blind prediction. 1 second, this is not the right one. Let's do it again. Should have 1 second.
SH.
No. This shouldn't look like this.
116, 253.
Yeah, but do you have the one in your email? Maybe I didn't copy it. Let's not show it. I don't want to show it now.
I'll go there.
I think we can go with that. That's fine. It's a minor change. That's okay. We'll just go with that one. Yeah, I think it's fine. So this year it was a joint effort between ETH, which they have had designed the test specimen, and it was tested in University of Bristol. So I will invite Michaelis to give the background of the competition, and then there will be a few other speakers. So
thanks. So the tests were the structure, this rocking podium structure, was designed in the ETH by Professor Stojadinovic and I. It comprises an aluminum slab which is supported by 4 columns which are allowed to uplift and rock in 3 dimensions, like wobble. But they are constrained with these conical constraints over there, not to move out of their original position. We shook this table, this wobbling table. We shook it 200 times. Why 200 and not 2 times? Because usually when you design a structure, you design it for many earthquakes, not for 200, but for more than 2, and because we can, okay? Like, this is a resilient structure, so once you construct it, whether you shake it 2 times or 200, it doesn't make such a big difference. We invited many teams to predict the maximum displacement. Now, we could have asked for the displacement at the middle, but this means that if the table rotates, it would collapse with a 0 displacement at the middle. So we asked for the average displacement of the 4 columns. I forgot to mention that the tests were conducted at the University of Bristol, and they were supervised by Professors Milonakis and Professor Sextos. So now these 200 ground motions were 2 sets of 100 ground motions. Each set was simulated based on 2 different seed ground motions. One was the El Centro ground motion, and the other one was Chichi ground motion. And what we asked from the contestants was not to give us the displacement response motion to motion. We just asked the CDF of the maximum of the response, because in the end this is what you design for. Whether the maximum or whether the median value comes from one ground motion or the other ground motion, it doesn't matter for the design. What you care is the statistics of the response. So this is how we evaluated the contestants. We had 13 teams from 10 different countries, and for each team we measured the difference of the 2 CDFs, the one they provided and the experimental one, the vertical distance. This is the Kolmogorov-Smirnov distance. The statisticians prefer it, but we could have asked for the horizontal distance too. And for each of the for each contestants, we added the two errors from the two sets of ground motions, and this is how we ranked them. Professor Stojadinovic will announce the winners.
Well, I'll announce one of the winners. And so let's try this. The second place, we'll have to start somewhere, so we'll start from the second place, was won by a team from Berkeley, of course, that consists of, well, these guys worked with Professor De Jong. Let me just read the names of here because they're full. So Daniele Malomo, Anjali Melhorta, and of course Matthew De Jong. And so what? Okay, so one of you, whoever is a delegate, come over because you've got to present. First, he'll show you guys what they did, and then they'll get one of these.
Great. So just a few slides. All right. So despite the complexity of the experiment, actually we've used a quite simple model based on the distinct element method, in which rigid blocks are connected by nonlinear springs, and we've used a more Coulomb criterion with no tension, so dry joints. And no artificial damping has been introduced, and that also helped in terms of runtime, so it was computationally much more efficient. And so in this case, each structure component has been faithfully reproduced numerically, and included the conical restraints, so in blue color. And we have assumed that the top and bottom slab were rigidly connected to these restraints. And in this case, the system nonlinearity has been lumped into column-to-restraint interface springs. You can see those are basically the black dots on the right of the slides. So thanks to this simplified modeling strategy, we were able to obtain results in a reasonable time frame, I would say, which is challenging in the discrete element framework. And so apparently we did fairly well. So thank you.
So then Daniela will get all these 3 plaques.
Great.
To deliver to all the other team members of the team. So congratulations again.
Thank
you for taking part. Thank you.
We can skip it.
All of us? 3 of you.
The 3 of you take a photo.
Is it mine?
Yeah, you. Oh, okay.
Okay, let's take 3 because there are 3 of you.
Can Photoshop them.
Yeah, exactly. So we get a pixel each. Huh?
Thanks again.
Thank you. Since the second winner was from Berkeley, I couldn't announce that. That's illegal. So the first place was from University of Toronto, and Myron is here. Please come on in. So Professor Christopoulos and his student Myron did the best prediction of the experimental results. Selim have been very helpful with the ETH team in setting the rules and following up on the submission. So we will submit the award together. So since it's only Myron here, so you can also have the 2 of them.
3 of you.
3 photos should be 2.
One for each of us.
Thank you. Congratulations.
Okay. Thank you, everyone. I'm very honored to be here, and I'm very grateful for Pierre's invitation. It's actually my first time in California. I've been having a wonderful trip and a very inspiring learning experience. So a big thank you. Now I'm just going to briefly talk about the modeling approach and some findings from this contest. So for this analysis, we decided to use Abacus as the modeling platform. And what we did was we first recreated the structure using SolidWorks in 3D to capture the exact geometry of the structure, because for rocking motions, the geometry is very important. And then we import the model into Abacus, and then created a detailed FE model where we applied some interactions, like contact interactions between rocking interfaces. And during this modeling process, there are many modeling assumptions we have to make. After we made the first model, we ran a quick push-pull analysis and checked with our hand calculations just to see if our model is reasonable or not. And then before we started with the dynamic analysis, the study was preempted by some sensitivity analysis. We were looking to many parameters that we think could potentially affect the rocking response of the structure. So I will be attending the poster session tonight as well to present more details. On the right here are the results of 200 ground motions, and below are some sample responses. Where in the first one, we call it a small amplitude rocking response, where you can see a permanent displacement drift because of the sliding happening between the top slab and the rockers. And the bottom ones where the lockup mechanism came to engage. So for the last slide, I'm just going to play a quick animation for one of the. Okay, yeah, it's working now. So this is how one of our analysis looks like. It'd be really interesting to see how these compare with the actual test results. Yeah, that basically concludes my brief introduction. Thank you very much again.
So yeah, these are wonderful activities that we like to continue doing. So if you have a cool experiment and you would like to put it out for blind prediction and you haven't published the data yet, please let us know. We have a very nice mechanism on how to prepare the material for that. We will work with you in terms of what you think is the important criteria so we can evaluate the contestants. We have a pretty well-established process in how to announce things. Mainly, we will need to put it out sometimes around September so we can give the contestant a month or two, depending on how hard the problem is, so we can get results evaluated, inform them, and you have to factor in some time for them to buy their ticket and fly from Canada or like last year from Japan, and so they can attend the annual meeting and you can applaud them.